they can put how many? 20 billion or 50 billion of transistor. You see that making it small is still useful, right? Now you can have 50 billions of transistor. You can do a lot of things. That is Moore's law, right? But at the same time, the interconnect is where has a very dominating role. The capacitance we discussed last time, right? And also the resistance. We'll discuss more in chapter 9. So what is the problem? All this I given are just old technology, but it is the same. And I want to introduce some important concept. It's about the IR drop, right? For example, let's look at this one. It's just a different processor, right? You see that when you go to a more advanced technology, the supply current increase, but the supply voltage decrease. Then what does it mean? It means when we go to a more advanced technology, the IR drop, which is equals to I times R, right? Increase because you have higher current. Then the voltage available to the circuit is going to decrease because it is VDD minus I times R. You have much larger current, then your power rail is deliver a very huge current. There will be a potential drop, IR drop, ohmic drop. So the voltage you get is no longer VDD. Let's take an example here. Right. For example, if this VDD, like this from the power supply is 2 volt, let's say 1 volt, okay? And then you have a current going through here. Then what is the VDD that you get? It's going to be VDD minus I times R dash. For example, it can become 0.9 volts. You see that? Because the source, yeah, you put your battery is 1 volt, but then because of the huge current, when you reach this inverter, it only supply 0.9 volt to it. And it's the same for the return path. This is ground. This one can be 0.1 volt because you draw a lot of current in this process and you have a large resistance in the power supply line, right? So it's just saying that my inverter is not really the inverter we are expecting. You know, my inverter only have 0.9 volt here and only have, and it does not reach the ground. It's only 0.1 volt here. So if I have signal come in, it will give me only 0.9 and 0.1. Now then this 0.1 comes to here. And this is a domino log. This is a dynamic logic. I expect to have 0, then there will be no leakage during evaluation. But because this is 0.1, it will increase the leakage, right? Because remember, right, if during evaluation, right, let's say we're doing evaluation. If you remember the IV curve in log scale is like this. Now, because of this one is 0.1, then it means originally the leakage is here, but now it shifts to here because you have 0.1 of VGS. So you can have maybe how much? If the subthreshold slope is 60 millivolt per decade, this one costs more than maybe 16 times. Not 16 times. It's almost turning off, right? Sorry, I'm wrong. It's about at least 10 times of more leakage current, right? If subthreshold slope is, let's say, 0.1 volt, I just call it 0.1 volt, then you have 10x leakage. Right? So you may discharge this information and then you corrupt it. Or in other case, you increase the leakage current. Is this part okay? Any questions? They are all very simple. You learned them already, but now you need to connect all the puzzle together, right? About our job, when you see this symbol, you understand this is going to VDD, this is going to ground. You in your brain, you will draw this circle. You understand this is VDD and ground. Then you know immediately this is only 0.1 volt. And then now you know that this is a dynamic logic. I increased by 0.1 volt. What's the big deal? It's smaller than VTH. No, nothing happened. No, because you already learned the subthreshold slope, right? That you increase by 0.1 volt, you may actually increase the leakage current by 10 times. Is that clear? Okay, but here I would like to tell you something called sheet resistance. I don't know if all of you know about it. This is about the resistance of a layer. It's talking about ohm per square. So what does it mean? If I have a resistor like this, a square, this is W, this is L, right? You're looking from top, right? This is a top view. It's just like when you're doing your layout. What is the, and I say this is the equals to R square. Okay. Then, can you tell me what is the resistance of this one? I did not draw it well, but they are all square. What's the resistance of this one? If I apply the voltage here, plus minus. If this small square has a sheet resistance of R square, what is the resistance of this one I just drawn? Well, the width is still W, right? But the length increased, correct? Right, so this resistance is just equal to R squared times 2 divided by 1, which is 2R squared. Is this okay? How about this one? What is the resistance of this one? Current is here, right? Assume the current is going in here. What's the resistance of, I drawn a, that is double the width and double the length. What's the resistance? Anyone want to help me?
Just R squared.
Just R squared. Why?
Because width and length both are increasing same.
Yes, because you multiply by 2 divided by 2, right? So this is R squared. Okay, so shear resistance is something you always use to communicate with the circuit designer, because for them, all they can do is just arrange the width and length. They cannot change the value. For different layer, they can have different shear resistance, right? For metal layer, they have smaller shear resistance. For the diffusion, they are larger, right? So there was student also asking earlier, should I use poly to do the routing? I use metal. It all depends on the delay you can afford, right? Using poly, you have smaller area because you don't need to go through the weir, but you have larger resistance, right? So that if you check this, the design file, right, you will see that the poly has larger shear resistance than metal one. Okay, so for example, here, if I tell you there's a process with a something with shear resistance equal to this, first of all, what is the resistance of this device? This is like our power device. It's 2 cm long. It can be like that because think about your chip is about 2 cm, right? If you only supply the VDD from one side, it needs to travel 2 cm. And if I only assign 1 micro, the width is 1 micron, right? what is the resistance if the sheet resistance is 0.07? Like what you just said, 0.05 times, or your very long 2 cm, which is 20,000 micron divided by 1 micron. Okay, so what is the size, right? 1, 2. So this is talking about 1 kilo ohm. Okay, then what is the IR drop? If your cable, if your power line is delivering 1 milliampere, then it is talking about 1 volt. Come on, my VDD may be just 1 volt. If you don't, if we do something so lousy, when you reach the other side, it dropped by 1 volt already. You don't have VDD supplying to the others. Of course, it's all approximation, right? When you drop by that much, you won't have that much current. But this is just telling us IR drop is very important nowadays. So we need to use different things, right? Let me remind you something after I talk on the next page, but do you have any questions? So shear resistance is something very important. I hope that you can know how to calculate, right? Maybe I even can test in the exam. I have not decided yet. Right. What can we do? Well, you can have all the power line going vertically, but it's not as good as we have a dual layer. I supply, first of all, right, just now what I'm showing you is like only one power from one pin to everywhere. But here, see, for every line, we have one power line. So it will be good. At least I don't need to traverse the diagonal. Second, why don't I have all the power line vertically and horizontally, right? Then if I am at this point, in the past, I need to wait until it drops from here. Now it will just go from here. And also I can supply from the top and bottom, right? If you have something so critical, just at the power plates, the whole metal plate is a power line. This one is large because I only have 1 micro wide. Now I make it so big. That is great, right? What are the drawbacks for all of this? Nothing is free. Each of this power, you need a pin. Pin is very expensive. You have limited pin. Second, they're going to create a lot of capacitance, right? So you need your pins, and then capacitance, parasitic capacitance is going to increase. You need to be very careful. Okay. Another problem of nowadays, what we are facing is more like reliability issue, right? This is something good to know. If you do any circuit design, you need to pass the reliability check, right? We did not do that here. But if you do a realistic design, not just DLC and LVS, you need to go through all the corner check. You need to go through all the reliability check and other things, even the EMI check, right? So reliability is what? When you have a very huge current, the electrons are running so fast, they knock off the atom. Okay, the atoms are supposed to be still, right? And then you pass a big current, then the electron keep knocking the atom off. And then you will start creating a void. This is the void. And this process is enhanced if you heat up. Now think about if I have a void, it means the resistance is even higher. Then all the electrons will keep knocking the narrower region like here, right? And you see, this is an experiment. They really pass through the current through, I think it's copper wire, and observe under SEM, electron scanning microscopy. And they do see that after a while, a void will be open. Once it opens, your signal is disconnected, right? So that's all I want to say here. It's also related to the how you route it. So that's why in those design rules, I forgot the name, but for cadence, they have a, for mental graphics, they have a name, for synopsis, they have a name, but it's related to this electromigration that you need to follow. So for example, sometimes you are not allowed to put the metal on top of you would rather to let the current signal to go from here to top instead of top to bottom, because this is going to have different electromigration and different reliability. Okay, so all you need to know, just pay attention to this. We are not teaching this, and actually I don't know well how to do design with reliability, but this is very important. Okay, any questions?
Is this little graphic here showing the void
Are you
growing?
talking about this one?
Is that the void?
Yeah, so here is the conductive. This is not exactly, because this is more like 3D, but here they just have a simple 2D metal. And then this, let's say this is copper. And they just showing that when you have a very small constricted area, you will, just by passing the current, you will break this bridge, but not the void here. For what I know. Okay.
Okay.
But electromigration is fine. Okay, now just now we talk about how to about the power, right? But also the same for delay. Hey, if in particular later we talk about SRAM, they have many cells, right? How am I going to drive this cell? Right? So how am I going to drive the transistor? So here are the transistor are here. Right? I want to drive this transistor, but they are very long. Okay. So what we do is that we use a metal. This has a low resistance to bypass it and then drive from both sides. Is that useful? You might say, hey, just originally, right? If I only have one driver, if this is L, right? If this is L, the time, if I only have one driver from left, right? It takes L squared proportional to L squared time. Take the time proportional to L squared to reach the right. Make sense? If you remember the distributed model we have learned before, each of them has a resistant, a capacitant, parasitic. So you take L squared. If, right, I have two drivers, it takes how much? Then it only takes L over 2 squared to reach the middle. Right? Because now the furthest distance from the driver is the middle. I assume this is so fast, like in light speed. They are driving from left and right at the same time. Right? So you reduce the delay by 4 times if you add the driver from both ends. Not 2 times, 4 times. That is a big deal, right? Think about you increase your frequency from 200 megahertz to 800 megahertz. Your product will sell very well. Okay, so that is called the metal bypass. From both sides, right? Not metal, but it's similar to metal bypass. Another thing is using this metal bypass. So this is poly 9. This has high resistor, right? So like in DRAM and SRAM, right? If I have so many cells, I don't want to drive the word 9 from the left through the poly. I use this bypass. Okay, so for example, if there are 1024 cells, right? So originally the time from driving from left to right is proportional to 1024 squared, right? There's a scaling, but proportional to this. Okay, but if I do a bypass so that every 16 cell I have a metal, right? Then what does it mean? It means that I'm going to drive from here and here at the same time, right? We assume the metal is very conductive, so no delay. Here, I need to drive all the way for 124 cells. Here, how many do I need to drive? Only 8, right? 8 from left, 8 from right. So what is the time to apply the signal, for the signal to reach all the cells? Same for here, right? 8, 8, right? So this T is proportional to 8 squared, not 16. Okay, so the speed up is going to be 1024 squared divided by 8 squared, which is to the power 14. Oh, that is a lot. Of course, that exaggerate, but because you are not exaggerate, this is reality, right? You just see that if you have DRAM, you have a 1024 cell, you try to rely on the poly to drive everything, it takes for you a very long time to drive. Then your speed is very slow, okay? So this is a technique to reduce the RC effect. Any questions? If no, then you can even say, how about we insert a repeater in every cell, right? So without repeater, right? You remember this is nothing but just V in and then R divided by M, right? And then you have the capacitor C divided by M. And then you still have this R divided by M, C divided by M, right? All the way to V out. Then you have a certain delay. Okay. Now, if you have the repeater, what is the delay? The delay becomes this one. First, you have M delay due to the buffer, the repeater. This is due to repeater. And what is the delay if you know, right? See if you can recall. What equation would you use for the delay? Right, it's just the inverter delay, TP0 times 1 plus F divided by gamma, right? So they are all related. You are able to find out what is the buffer delay. Okay, and at the same time, you have this distributor wire distribution delay. Right, system, right, wire delay. Right, which we have learned earlier is 0.38 RC. RC is per unit length times, because each of them is L divided by N, so L square, and then you have M of them, so times N. Right. So how many buffers should I insert? You can imagine if I insert too many buffers, it's going to make the delays too much, because all buffer has a lot of delay. But if you don't insert anything, you also know that this one is proportional to L squared, right? If we can make it L divided by M, then that would be great, right? If M is very large, but at the same time, the buffer will increase. Okay, so what we do is that we do this, partial TP, partial M equals 0. And then we find out that the optimal number of states, this is the optimal number of states, is this. Okay, this is just an equation and I'm not going to derive it, right? If I want you to do this in exam, I will provide the equation, okay? You even don't need to copy from the cheat sheet. But the problem is that you need to appreciate what we're talking about. If you have very long wire, it's proportional to L squared, which we proved in the first part or second part of this semester already. And how we solve this problem? If that wire has very huge resistance and for some application purpose, the easiest is to bypass. I use some low resistance wire, and then I can reduce the delay a lot. But if this is a clock, what's the point of bypassing? I'm also already using the metal one. I can add some buffer repeater, because the repeater can help me to speed up the process. Why? Because when it is not so long, the delay is L divided by M squared. So if M is infinity, I don't have delay to this wire. But of course, then I have infinite number of stages. Each new repeater is going to increase delay. And how many should I use? I should use M equal to this equation. Okay. Is this clear? Right, so this is an issue about the interconnect. And okay, I think my notebook. Okay, so any questions? We are done with the interconnect, some of the selected topic. If okay, then I will go to the last topic about SRAM. Okay, if I assume you are okay. So what is SRAM, right? SRAM is the cache. We usually call cache, right? SRAM is just